Okay, students, good morning again. Yesterday I put online the video of last Thursday. I had to post-process it, so it took some time. It should be okay, and it's available on YouTube, still not available in Panopto. I just realized now that I have to put it also in Panopto, but should be there. And it will be also in Panopto shortly. Now, I think we can move forward. I think last time we got more or less at the point of the equation that you see on the screen, which is describing the fraction of a catchment, of the considered catchment, that has a soil infiltration capacity that is lower than a given value C star. This is what we discussed last time. Just to make a brief recall of what we did, we are talking about rainfall runoff modeling, deductive assessment of water resources availability, and after talking of inductive methods, we turned to deductive, and we studied the rational formula, the linear reservoir. We made a brief mention of the nonlinear reservoir, and now we are introducing the IMOD model. IMOD, which is, we said, a very nice idea, an interesting idea to describe the spatial variability of the water storage within the catchment. And therefore, I said that the idea is to describe the spatial variability of storage in a statistical way. So we are not describing where we have a given value of water storage, of potential water storage. I call it also soil storage capacity. We are not aiming to describe where I have a certain water storage. We aim to describe the fraction of the catchment that has a water storage that is lower than a given value. And this given value, we are talking about potential water storage into the soil, should range between 0, because the minimum is 0. We can't have a negative water storage. Should range between 0 and a max. The max is C max, and if we give a value of C star that is ranging between 0 and C max, a value of soil water storage, this relationship tells me what is the fraction of the catchment where I have a soil water storage that is less or equal than C star. Okay, so this fraction is varying from 0 to 1. It's a fraction of the catchment. In fact, you see that we said that if I give to C star the value of 0, here I get that the fraction of the catchment that has a lower or equal water storage is 0. If I give a value C max, the fraction of the catchment that has a lower or equal water storage is 1, because everywhere in the catchment I have a soil water storage that is less or equal than C max. And we said that here I have two parameters, C max and beta, describing this the progress of this fraction against what? Against C star. And we said that depending on the value of beta, we can draw graphs of the progress of the fraction against C star. C star is on the horizontal axis. The progress of the fraction against C star, depending on the value of beta. And I said if beta is equal to 1, then the progress is linear. If beta is equal to 2, I have a function with concavity that is oriented towards below. And if beta is less than 1, I have concavity that is directed to above, to the upper direction. What happens if I have beta that is approaching C max, or it's equal to C max, and what happens if beta is approaching 0? Now, you see that if I have beta that is tending to infinity, the fraction goes immediately to 1. For increasing C star, the fraction gets immediately to 1. What does this mean? It means that the water storage into the catchment, just for small values of C star, is lower than that. which means that the water storage into the catchment is very low. If conversely, beta is approaching 0, I see that the fraction remains 0. So the fraction of the catchment that is a lower water storage is 0, which means, which means that the basin is impervious if beta is approaching 0. And then there is a sudden convergence close to Cmax to 1. Now, how are these figures obtained? And this is the subject of the box that you see here. Basically, the box is just for your interest, is an IMOD function which creates the graphs above. It's reported here for your interest. So you see that it's very easy, it's very short. You can cut and paste it into an R console and you reproduce the graph. What is the purpose of giving you this box? The purpose is just to give you some additional knowledge on R functions, how plots are obtained into R, and also to give you the opportunity to play with the numbers in this, to play with the parameters in this relationship that gives to you the fraction of the lower water storage into the catchment. Because by playing, you understand better what's going on. And you see that the function has two parameters, because we have two parameters in the relationship. And the two parameters are beta and Cmax. And then you can change. Cmax is given a default value. So I suggest that you don't change it, because it doesn't make any difference in the shape of the graphs. What makes the difference is beta, is the value of beta. And you can run this function, and you can get a beta. If you assign a beta equal to 1, you get the plot, and the plot gives to you exactly what you find in these figures. And just let me show you, there is no need for you to repeat. Just let me show you by opening an R console. I don't need RStudio here. Let me see. I just open an R console. And what I'm doing, I clear the screen. I'm just cutting and pasting. So I go into the website, I take this, I select it, I copy it, and then I go here, and I paste it. Paste. This is the function. Then I can write IMOD 1, and this is the value of beta. And you see I get the graph that you see on my web page. Very good. Now I can type IMOD 0.5. See, I got the other one. IMOD, let's say 1000. And you see that I have, let's reflect on this graph, what this graph is telling to me. For a C star that is close to 0, let's say C star equal to 1, I already have a fraction of the catchment that has a lower water storage that is equal to 1, which means that indeed the catchment is impervious. It's impervious. Almost all the catchment has a storage that is lower than 1. It's impervious. So I'm correcting what I said before. You see that by reflecting on what I'm doing, I can get it. And then if I put the beta very close to 0, you see that even for increasing C star, the fraction of the catchment that has a lower water storage is 0, which means that everywhere I have a higher water storage, the catchment is very water retaining. And then, of course, when I get to Cmax, it goes to 1. So everywhere I have Cmax. If everywhere I have Cmax, it means that I have this graph. Instead, if everywhere I have 0, I get this one. You see, it's extremely easy to play with it. You may wonder, I open a parenthesis and then I close it in 30 seconds. You may wonder why why Montanari is so insisting on playing with the codes. The reason is precisely what Thomas Guinan explained to you last Thursday. I think the presentation by Thomas clearly demonstrated that several companies, several institutions, several public bodies look for people that can make programs. They have a problem. The problem is I have data. I have to make the data publicly available to everybody. The problem is that people is not able to download their data. Why? Because they need to make a program in Python. And they don't have the opportunities, the internal opportunities, to make the data more easily available, more user-friendly available. So they look for people. Why they give 5,000 euros to people to make programs? Because they want to identify people, clearly, that students and then professionals that can really make programs to use their data. And of course, if you win it, then I bet that probably they may say, would you like to get a scholarship in the future? And then they try to test you again. So I think this is a clear demonstration that being able to make programs is useful, even in this period where we have the feeling that everywhere, everything is already prepared, okay? We have the feeling that we can use commercial programs. Actually, they are looking for people that can use Python, which is an open source, which is not user-friendly, can use Python to make their data available. So this is the reason why I insist, because it's not difficult making programs. If you are here at your master degree level, it means that you have the skills to learn things that are much more complicated than making programs, much more. And then I am sure that you have the capacity. The only thing that you need is the will to make something that is not strictly required. At the exam, I will not ask you these things. So you are not strictly required to learn it to get your degree. So the temptation is that let's forget what is not really useful to my target, and which is not wrong. I mean, to get your degree, you have to focus on what is required. But on the other hand, your target is not the degree. Your target is after the degree. The degree is just an intermediate step. So just try to get used to this, to look at your future, not at the immediate target. You don't have to look at the next one. You have to look the next. And in order to do that, you can try to get the most from the opportunities that the university is offering to you. I think this is the biggest mistake that students do. They focus on getting the degree. But the degree is the start, it's not the end, I mean. Okay, if you focus on something that is the end, it's always a mistake, even if you are 90 years old. Okay, let's go on. So I hope you understood what is the concept here. And I go back to this relationship. The concept, it's a very nice idea. I want to describe the spatial variability of the soil infiltration capacity in a lumped model. It's still a lumped model. I am still considering the catchment as a whole with a unique rainfall, but I want to consider this variability. Why the variability of the soil infiltration capacity is important? We already discussed it, because where the soil can take and retain water, it's a soil that reacts slowly to precipitation, because storage is like a spring, you know. It takes water and then it releases it slowly. Where the soil cannot retain water, you have an immediate reaction to precipitation. So if you are concerned about floods, you are a bit concerned by this type of basin that doesn't retain water. But even if you are concerned about water resources, you are equally concerned by a catchment that doesn't retain water. Think at dams. Why we build dams for water resources management? Because we want to store water. But if I have a natural storage, that's perfect. I don't need a dam. Dams are often constructed in places where the storage of the catchment is not enough, which means that during the summer, in our climate, you have low flows. During the winter, you have high flows. And these high flows are originated because the catchment cannot retain water to release it during the summer. And therefore, what we do is to build a dam, which is a substitute. I'm simplifying the concept, but I hope you understand. And then to describe the spatial variability is important. Okay, now the problem is that you can understand now what happens here. If I put rain over the catchment, what happens? What is the logical consequence, the logical step forward of this approach? The logical step forward is that where I have the soil that is able to store water, I have no production of river flow. The correct term is no production of runoff, and then the runoff converges into the valleys and originates river flows. So where I have soil retention capacity, it rains over there, and the soil acts as a sponge. A sponge, I don't know how to pronounce it in English, okay, sponge, and retains water. If it rains where I don't have infiltration capacity or the infiltration capacity is exhausted, then you have runoff. And we have to find a way to compute at each time step where I have water retention capacity and where I have not. And I am not interested in locating this position. I am interested in estimating this fraction. And beware what happens here. At the beginning of a rainfall, I'm trying now to explain physically what is the workflow of this model, and then mathematically. But it is important that you first understand physically. So let me just go to the blackboard. Let me de-share the screen for a while, and let me go to the blackboard with the other camera. Sorry. Let me change it. Good. Perfect. Now, remotely, you have the blackboard. So let's suppose that I have a catchment, okay? It's like a leaf, and here I have the river network, okay, which has branches, etc. Now, I am interested in getting the river flow here. This is what we call the closure of the catchment. We identify the border of the catchment by following the divide, okay? As we said, this is the way we identify the catchment area. Good. Now, let's suppose that I get some rain. Let's call it P, and or let's call it intensity of rain, I, P. Okay, very good. Now, let's suppose that I have a fraction of soil storage capacity that is 0, like here, okay? I don't know where, but I know the fraction. I know the extension in relative terms of this area. What happens here? It happens that here I have runoff production, and then something that goes into the river network. It will take some time. We will see how the model computes this time to get to the river network. And then I have a first component that goes down along the river network, which is given already at the first time step, because this IP is at step 1, like first hour, from the beginning of the event. Already in the first hour, from the impervious area where the C star is 0, where the soil storage capacity is 0, I have some runoff. Good. Furthermore, after 1 hour, I may have another part of the catchment here that was able to capture some water, was able to absorb IP, but after the first hour, it's saturated. Why? Because C star is lower than IP. So this fraction was able to capture water at the first hour, but then it's not able to capture any more water because it got saturated. How can I compute this fraction? Simply, I put C star equal to IP1 times delta T, because this is an intensity. So in order to get a length, the storage is measured as a length. We said in order to get a length, I have to multiply by the time step. I get a new value of C star, and then through the relationship, I compute the new fraction F C star, which now counts also this part. And then when I get IP2, I get the storage, the runoff from this area, but also from this one. Okay? Then next time step, I have an additional area that gets saturated. I have to compute another fraction and move forward. You understand that after some time, the whole catchment is saturated. How can I measure when the catchment is saturated? When the sum of the rainfall depth at each time step reaches C max. Because C max is the max water storage into the catchment. When the sum of each rainfall depth at each time step, which is called cumulative rainfall, when the cumulative rainfall gets to C max, then the next rainfall, everywhere in the catchment, there is a runoff generation, and the catchment is saturated. This is what happens. So you understand that we need to compute some integral here to compute finally the river runoff. Because I have to sum at each time step an increasing contribution, an increasing one. At each time step, I have to get a sum of first from here, and then from here plus here, and this is an integral, and then from here plus here plus here. This is what happens. And you may think, oh, this is much complicated. Actually not. Because this is also another nice feature of this model. You will see that the mathematical treatment is not complicated. But in order to understand the mathematical treatment, I think that you have first to understand this conceptual workflow. Do you have any questions? Yeah.
Is this the only way to calculate, to do this calculation, or there is another option? For example, the ways with soil mechanics can do it to determine the capacity of the soil that takes the water to keep it.
Okay. The question is this the only way to make this computation, or there is another option through, for instance, studying soil mechanics to estimate the soil capacity to keep water? So I would split the question in two parts, my answer in two parts. First, if you ask me mathematically, let's suppose that I know this relationship, which is, let me put it on the screen. Let's suppose that I know Cmax and beta K. Okay, let's suppose I know them. And then the question may be, is this the only way to make this computation, or mathematically there is another way? I don't know if there is another way. I think the way that I will explain to you is very simple, but if you have ideas to simplify it, you are welcome. And it will be a mixed analytical numerical approach, as you will see. And I think the solution that I will propose to you to apply in practice the concept that I put on the blackboard, I think it is it is very nice. But if you have ideas, there might be another possibility. And but your question, actually, I would also give a second answer. I think your question can be also reformulated in these terms. Given that I accept this relationship in its shape, can I estimate beta K and Cmax directly from inspecting soil mechanics, etc.? Because I think this is the meaning of your question. I think you are not questioning the shape of the relationship. I think the shape, it's not ideal to change it because we will see that this is easily tractable mathematically. So I wouldn't change the shape, but I think it is an interesting question how I estimate Cmax and beta K. And let me anticipate, because we will discuss this. Parameter estimation, it's an issue in any modeling procedure. It's an issue so far we discussed just briefly, but in any modeling procedure, usually you have parameters, and parameter estimation is an issue, how to make it. I anticipate that the usual route is to optimize the simulation with respect against the observed data. But you have to check that the value that the parameters take is physically meaningful, and how to judge it from soil mechanics, from geotechnical engineering, from comparison with other catchments. So I hope I answered your question. Okay, now we have to apply it. And let me go down in the presentation. And let's see what happens when a storm occurs over the basin. Let me just check. I think I have a PowerPoint presentation, yes, which is nicer to use. Okay, now we already discussed what is the implication of different beta K values. And now I need to move forward to assume that a rainfall event occurs over the catchment. The way we define rainfall during a rainfall event, is usually, if we look at the databases, they give you rainfall at a given time step. And they give you usually a depth. So for instance, you may download from the website of the Regional Agency for Environmental Protection here, rainfall data. And they tell you, these are hourly data, these are hourly rainfall depth. And they give you the unit. So usually it's in millimeters. Rainfall is usually measured in millimeters. And so you see a sequence of numbers, starting from, for instance, January 1st at midnight. And they give you 0, 0, 0, 0, until 8 p.m., you get 10. It means that from 8 to 9 a.m., or p.m., it's the same, 8 to 9 a.m., you got 10 millimeters. And then maybe at 9 a.m., you have 15, which means from 9 and 10, you got 15 millimeters, and so forth. And they tell you these are depth. Actually, they are intensities, because at each time step, they give to you the rainfall during the delta T. So you may be misled. You may think they are rainfall depth. Actually, they are rainfall intensities, because they are 9 millimeters per hour. And now there is the cumulative rainfall during the event. The cumulative rainfall is the sum of the rainfall intensities times the delta T. Okay, so if you have 9 millimeters per hour, and then the next hour you have 10 millimeters per hour, then you multiply by 1 hour, and you have 9 plus 10. The cumulative rainfall at 10 a.m. is 19 millimeters, and this is not an intensity, it's a rainfall depth. And you have to have it clear. You may think that this is a nuisance, it's not a big difference. I mean, what does it matter if I got 9 millimeters that I keep in mind that this is an intensity? The reason why it matters is that sometime you have to convert it. So if you see that you have an hourly rainfall data, and from another rain gauge you have daily rainfall, when you put them together, because you want to feed a rainfall runoff model, if you want to make the daily rainfall comparable with the hourly rainfall, you have to divide by 24. You have to assume that during the whole day, rainfall was constant, because when rainfall is given at a time step, there is no other way. During the time step, you assume it's constant. But to compare daily rainfall with hourly rainfall, you assume that daily rainfall is constant along the day, and you have to divide it by 24 if you want to put them together. And this is the reason of many mistakes that we do in hydrological modeling. And I tell you, after almost 30 years, when I start to apply a model, in my mind I say, oh my God, what is the unit here? Because otherwise I make a mistake. So you see millimeters in rainfall. So what is a number? What is the unit? It's millimeters, but it's millimeter per hours. Because then, when you compute the river flow at the end, you want cubic meters per second. So you understand that when you sum many contributions that are millimeter per hours, and then you want the result in cubic meters per second, you have to know the units. You cannot just sum the numbers without knowing that this is an intensity. Finally, the dimensional analysis, you can make it only if you know the units. And the dimensional analysis is a very useful tool to make sure that you didn't make a mistake and that you understood what's going on. So beware of the units. Okay, very good. Now it starts raining. So beware of the difference between rainfall intensity and cumulative rainfall. To understand how this model works, you have to have clear this difference. Okay, and now let's us introduce another symbol, C depending on time, CT, you see on this slide here. It is, look at the definition, the time varying water depth stored in the unsaturated location of the catchment. What is CT basically? It's cumulative rainfall. Let's read again the definition. It's time varying, okay, very good. Water depth stored in the catchment in the unsaturated location. So imagine again what happens. It starts raining, and you have the catchment that it's like a sponge. So the catchment takes water. And if it's not saturated, it takes all of it. So at a given time, what is the water depth stored in the catchment? Is the sum of the rainfall that I got. It's cumulative rainfall. But I have to make clear that I refer to unsaturated locations, because otherwise, if the storage is saturated, let's think at C star equal to 0, it cannot take water. What is the water depth stored in the catchment? 0. So it's not equal to the cumulative rainfall. CT is equivalent to the cumulative rainfall only in the unsaturated locations. But it is extremely important that I realize that there is a storage, a time varying storage into the catchment in the unsaturated locations. Why I use the symbol C? Because it's a storage, so it's comparable to Cmax, and it's comparable to C star. C star was an arbitrary storage. Here I use a different symbol because CT is not arbitrary. It's given by cumulative rainfall, if I refer to unsaturated locations. And let's also ignore evapotranspiration, because the water storage into the catchment is depleted by evaporation. Let's forget it for now. We will see that later on, we will need to take evaporation into account. Evaporation decreases the storage into the catchment, but let's forget it for now. If we forget evaporation and transpiration, which we put together in one term, evapotranspiration, which is a little bit old. Now people don't like, researchers don't like to call about evapotranspiration because they are two completely different processes. But they were grouped together in the past because both of them mean water depletion from the soil, and therefore they put it together. Let's forget it for now, okay? And then I can say that in the unsaturated location, CT is equal to the cumulative rainfall depth. And this is evolving during the rainfall event. Good. Now, let's look at this graph here. And just let me check one thing. I want to make sure that I'm not forgetting anything. Just give me 1 second. No, I'm not forgetting anything. Okay. Now, what is this graph? This graph is the same that you saw before. On the vertical axis, there is the fraction of the catchment, which has a storage less than C star, and on the horizontal axis, you have C star, which is varying from 0 to C max. Now, it's clear that on this horizontal axis, I can also place my values of CDT, which is progressing a long time. CT can only increase in time. If I forget any water losses, its cumulative rainfall depth, it can increase or stay constant, but it cannot decrease, okay? So what happens at the beginning of the event? Let's look at this figure, and who is in the room can look at the blackboard. At the beginning, we have a storage C, which is 0. Very good. And then I get some rain during the first time step up to time t. There is some rain. And therefore, this rainfall depth brings the storage in the unsaturated area to the value CDT. CDT is precisely equal to cumulative rainfall at time t. Can you follow me so far? Very good. Now, at time t, what is the fraction of the catchment that is saturated? I go up, I cross the red curve, I go on the left, and I get the fraction FCT. Very good. Okay, this is the situation at time t. Very good. Now let's move to time t plus dt. And let's try to understand what happens during that time in physical terms. I have CT that is progressing because I have some rain. It's progressing to the value CT plus dt. Okay, and then I can get a new fraction. The new fraction is FCT plus dt. Now, the difference between CT and CT plus dt is rainfall in time dt. Okay, rainfall in time dt. Now, this rainfall is partly absorbed by the catchment by a fraction that is between FCT and FCT plus dt. So the product of rainfall times a fraction that is in between CT and T plus dt is basically absorbed. And this rainfall absorbed is given by the dark pink area that you see above the red curve. Okay? And this is storage. And then I will explain better why the fraction above and not below. The fraction, the gray area below the red curve is the product of rain times the fraction of the catchment that is that is saturated. So if this fraction is, let's say, 0.5, you have rain times 0.5, which is half of the area of the catchment. This is runoff. What is above is rain times the fraction of the area that is a sponge, and therefore is storage. So what stays above the curve is contribution to storage. What stays below the curve is runoff. And you may say, I don't understand really why the product of rain times a fraction gives me runoff. The answer is easy. The fraction is fraction of an area. If you multiply rain, millimeters, which rained in the time delta t, so it's millimeters per time. You multiply it by an area, because the fraction is fraction of an area. So it's an area. You get length cube divided by time, which is flow. I mean, this is the most difficult part of the understanding of this model, the conceptual understanding. Because once that you understood, once that you got that this red curve is given by two parameters, Cmax and beta, good. And then I have rainfall, which is an input data. So if I use rainfall in the horizontal axis, because rainfall is equivalent to CDT, the result is that the area below the curve, up to time t plus delta t, whatever time, the area below the curve is river flow. And the area above the curve is storage. The area below the curve, what is the area below the curve? It's the integral. So I have to compute the integral of the analytical relationship that you saw on the blackboard before, on the screen before, and I get the runoff. So let's forget for now about this relationship, but you see an integral here, which is the integral between 0 and Ct, so between 0 and the rainfall value. The rainfall, at each time t, you get a cumulative rainfall. We said cumulative rainfall, I can assume it's the same than CDT. So the integral is between 0 and CDT, between 0 and CDT, of what? Of f. Now I call it key because it's the variable of integration. F key in the key. So I am integrating the relationship that you saw on the screen before between 0 and Ct to get this integral, which is precisely runoff. And then what is the storage? The storage is rainfall minus runoff. So I could also explain this relationship on the blackboard. I repeat, storage, WT, is rainfall, cumulative rainfall, minus runoff. And of course, this gives to you the cumulative runoff, the integral, the area below the curve, gives to you the cumulative runoff. Usually, we are interested in getting the river flow in terms of river flow at each time step. So actually, we are not interested in the cumulative runoff. If you want to know the river flow at each time step, we just have to make the difference between the integral at time t and the integral at time t plus delta t. But as I said, this is the difficult step. Then computing the integral is not difficult. Once that we got the concept, the area below the curve is the runoff, the area above the curve is the storage, then, I mean, this computation is easy. You will see that it's easy. This is a question that I ask sometimes at the exam. I consider it not a difficult question, but still, I mean, an important question, and sometimes I ask it, I'm a model, and usually if I see that you are well prepared, if I want to test really your preparedness, then I go with some tougher questions, and this is a question that I consider, yeah, well, not really tough, but okay. Okay, now the problem is that we understood that if I want to compute the river flow, I have to compute the C integral. If I want to compute the storage, I have to compute this difference. And now my problem is this integral. Any questions so far? Okay, let's compute the integral then. Oh, this is an animation. You know, I try to do my best to to make things understandable. And I think it is interesting to look what happens after saturation. After saturation, you have the basin that is saturated. So if you have rainfall that exceeds Cmax, it's, you see the black rectangle, it's surface runoff after saturation. It's just given by rainfall times 1, rainfall times area, because the basin is saturated. Because otherwise, if I didn't put this black rectangle, it looks like I can only model until I get the basin to saturation. No, I can continue. Afterwards, it's easier because everything is saturated. But also, there is another complication here, because I forgot deliberately, I forgot evapotranspiration. I have to put something there, because otherwise, once that the basin is saturated, I don't have any depletion of storage after the rainfall event. Actually, what happens is that when it stops raining, then the sun comes and you have evaporation and the soil gets drier. And I have to also introduce this. And also there is another thing that I just dropped at the beginning. It is the time taken by the runoff to get to the river network. You understand that I have also to model this delay. But these are really small additions. What is really, what I consider a bit complicated is understanding this mechanism. I just want to tell you that these kind of models were proposed in the 80s, when the computer programs were, the computing resources were not so powerful. And the people up to the 80s were still modeling with lumped models like the linear reservoir or other variants of the linear reservoir, like the nonlinear reservoir. When this idea was proposed, which was not very computer intensive, because you will see that the code is very short, and this is the nice feature, this was considered a milestone development. Because, indeed, this model, the IMOD model, is still widely applied, widely. Most of my research papers, I would say that all of them in the past 15 years, I applied this model because it performs really well. And there are other models that are, of course, more evolved, more developed, but they are also much more complicated. This one is very simple and very fast, because we also have to look at computational requirements and time taken by the simulation. This is very fast. You will see. Okay, now let's compute this integral. Don't be concerned, it is very easy. I could also make it on the blackboard, but let's try on the screen, because on the I think on the screen is better for the students that are remotely assisting. But I don't think this slide is nice, because it is too scary. Let me just get one by one, if I can. Not really, but let's focus on the first one here, which is precisely the integral between, let's look at the first line above, integral between 0 and Ct of f, depending on a variable of integration key, here in the key. Okay, very good. Now, I just substitute with the expression of f, and just let me go back to the web page. F is given by this. So I have to just to plug, instead of f, this relationship here. But of course, here I have C star, and when I plug in into the integral, I need to substitute C star with the variable of integration. This is the only difference. But if you look at here, is 1 minus key divided by C max, elevated to the power of beta k in the key. Just a substitution. I put it there. And this integral, fortunately, is easy to be resolved. This integral, the left-hand side is just copied from the first line. Now look at the middle line. It's given by, there is integral of 1 in the key is key. Very good. Plus the integral of 1 minus key divided by C max to the power of beta k is given by C max divided by beta k plus 1, which multiplies the same quantity between square parentheses, and now the power is beta k plus 1. If you want to check it, just compute the derivative. The derivative of key is 1, and then the derivative of the second addendum is exponent beta k plus 1, which then annihilates with the denominator of C max divided by beta k plus 1. And then is given by C max, which is a constant, and you keep it. The integral of the quantity between, the derivative of the quantity between square parentheses in the middle line is equivalent to the same quantity between square parentheses, but you have to multiply it by minus 1 divided C max, which is the derivative of the second addendum between square parentheses. And then the minus gives to you back the minus sign that is in the first line between the square parentheses. And the C max annihilates with the other C max. The power from beta k plus 1 becomes beta k, so you see that if you compute the derivative of the middle line, you get precisely the argument of the integral at the first line. So you see that the integral was easy and is to be computed by between the extreme of integration, 0 and Ct. So if I just substitute in the middle line the extreme of integration, I get the third line, the bottom line, which is what we wanted to get. It's our integral. You see that it's very, very easy. And what is the result of this integral? Remember, it's runoff, cumulative runoff, up to time t. Cumulative runoff up to time t. But if I wanted to compute the storage, because also the storage is important, we will see in the application, I need the storage. Why I need the storage? I want to anticipate this. Because at a certain point, the catchment becomes, at a certain point, I have to subtract from storage the evaporation. And therefore, it's not just enough that I compute the runoff. I also need to compute the storage, because then I have to update the storage with the evaporation. This is the reason. And what is the way to compute the storage? I go back, just 1 second, in my presentation. I go back. What is the way to compute the storage? Ct minus the integral. I have the result of the integral. Let's then subtract, let's give the minus sign to the result of the integral, and let's add Ct, okay? Now I go back here, sorry. I go back here, and let's move forward. Here is the storage, which is given by, this is not really, there is a step that I bypassed here, and then we go back to this, not this, but this. Okay. From this result, I have to compute now Ct minus the integral. So the result of the integral is in the third line, right-hand side. Now, if I compute Ct minus Ct, they annihilate. And then minus Cmax divided beta k plus 1 times the square parenthesis. And then there is the last term, which becomes a plus. Now I can move to the previous slide. You see the plus here, Cmax divided beta k plus 1, minus Cmax divided beta k plus 1 times the quantity between square parentheses at the power beta k plus 1. It's just a subtraction. And it would be nicer if I did it on the blackboard, but I hope that, on the blackboard, who is following from home, it's more complicated. So I hope that you got it. And then I can take the common factor, Cmax divided beta k plus 1, which multiplies 1 minus the square parenthesis to the power of beta k plus 1. So the result for the storage is quite easy. But of course, these computational steps are not complicated, but you require some capability to manage mathematical developments. It's not a big deal. Anyway, I am sure for you. Okay, I think I can forget about this, and then let me go back to the PowerPoint. So you see here, this slide condensate all the results. I have, look at the screen, at the screen, yes, remotely and on the physical screen in the room. What I have is the third line on the left, result of the integral, and then fourth line on the left, result of storage. So computation of storage. One interesting thing, what is the max storage that I can get in the catchment? You may erroneously say it's Cmax. No, this is an average storage. I'm talking of what is the average storage into the catchment. Cmax is the max storage in the catchment. It's a storage where I have the max of the water retention capacity. But WT, what is indicating? It's indicating the average storage over the catchment. And let's suppose that the catchment is saturated. It means that rainfall reached the value of Cmax. The storage in the catchment is not given by Cmax. It's lower. Why it's lower? Because there are some areas where C is lower than Cmax. And therefore, WT is an average value. There are some areas that don't retain water. There are some areas that retain Cmax. WT is the average storage. So what is the max of WT? It's lower than Cmax, of course. And it is easy to be computed. It's just sufficient that you substitute Ct in this relationship, the last line on the left of the screen, which the relationship that gives to you WT depends on Ct. Let's give to Ct the value Cmax. Very simple. You plug in Cmax here, and then you look at the square parenthesis. 1 minus 1 is 0. And therefore 0 to the power of beta is 1. And therefore, between the curly brackets, you have just 1. 0 to the power is 0. 0 to the power of beta k is 0. So between the curly brackets, you just have 1. So Wmax is simply equivalent to Cmax divided beta k plus 1. And beta k plus 1 is for sure greater than 1 because beta is greater or equal to 0. It's greater than 0, actually, beta. And therefore, you have Cmax divided by something that is greater than 1. Maybe close to 1, but greater than 1. It means that Wmax is lower than Cmax. This is interesting. Okay, And then there is a further relationship here that you can see on the right, in the middle of the screen, which is basically an explicitation of the value of CT depending on WT. So if you take the expression given to you WT, the last one on the left, and you derive from it CT, you get this explicit representation. You may say, why are you getting it? Why I am interested in CT? CT is rainfall. We will see that in the application it is, we need also to compute CT in the application of the model. So this is why this relationship is there. Now we have everything we need to compute storage and runoff and also CT. So this is the purpose of this integration, to compute, again, at each time step, storage, runoff, plus, for some reason that we will see later, CT. Good. Now, before going to applying the model, before going to the code, now we need to remove some simplifications. We dropped the delay time to get to the river network, and we dropped the evapotranspiration. So we have to, in a way, to introduce, to model these two processes that we don't have considered so far. These are simple additions, of course, I said, but still, I mean, the development so far has not been so simple. Even if we make simple additions, we complicate it a little bit more. So I ask for your patience and understanding to just tolerate me a little bit more. And this is the classical scheme. When the model was presented, the author proposed this scheme to depict it by including everything, by also including delay time and evapotranspiration. Let's try to understand it a little bit. And let me tell you a curious thing. This model was proposed within a PhD thesis, never published in a paper. It was, now, when we reference this model, we reference the papers that used it. Not for the first time, because for the first time it was used in the PhD thesis. Actually, I think that probably the authors didn't realize that it was a good idea. And the reason why he didn't realize it was that he built on previous models that already used this idea, but with a different relationship for FC star. And actually, this development, IMOD, is much more interesting than the previous models. But probably he didn't realize it. So now we reference the PhD thesis, but the PhD thesis actually is not available anymore. And because it was a PhD thesis that was presented in 2000. So it's interesting because sometimes, I mean, the progress always comes by superimposition. The great ideas, I already mentioned this to you, like Einstein, I already said this to you. Einstein proposed the theory of relativity by building on the work of Lorentz. And so it always comes in this way. But the result is that sometimes we don't realize when there are interesting good ideas. And this happens quite often in science. The people that are celebrated during their life, that are most celebrated, not always are kept celebrated in the long term. And some people that are not recognized in the short term are recognized later. And this happens quite frequently. And it's interesting. Einstein is a person that was recognized during life and is still recognized today. So, I mean, there are also exceptions. On the other hand, there are several people that during their life are not recognized. And when I look at science today, I get the feeling that there are some people that are really making a step forward, but we don't recognize them. And this often happens when you go against the mainstream. When you go against the mainstream, people are a bit reluctant to accept this. And this is interesting. I think it is extremely interesting. But anyway, IMOD model. What you see in the left, the graph on the left, is precisely the graph that I proposed to you before, but it is turned around. So there is FC in the horizontal axis and CT in the vertical axis. So if you mirror it, you get what I proposed to you before. And with some differences, because I don't want to discuss it, but you see that the storage is here and the surface runoff is here, is above the curve. So you can recognize more or less the same. And here it's a little bit, you see there is 1 here and 0 and Cmax here, so there is, this is turned around. In my graph, 0 was on the left, was in the lower curve, so it's turned around, but it's the same graph. And you see that he basically proposes to split the contribution to runoff, which is above the curve here, it's this one here, in 2 contributions. One is up to saturation. After saturation, he calls it in another way. Why he changed the name? Because when you compute it, the computation is different. Because up to Cmax, you have to compute the integral of the curve. After Cmax, it's simpler, and it's a different story. So he wanted to separate it in the algorithm, and I think it's a good idea. Because, as I said, after saturation, you don't need to compute any integral anymore. And then he proposes to do this, that evapotranspiration at each time step is subtracted. So basically, it's subtracted from the storage. So at each time step, we need to compute the storage and subtract something. This is why I wanted to compute the storage. I have rainfall entering into it. I mean, gross rainfall, because evapotranspiration is removed later, gross rainfall. And then he said, let's take the runoff and divide it into components through a parameter alpha. Alpha is ranging between 0 and 1. Alpha is a third parameter of the model. The model so far counted only 2 parameters, Cmax and beta k. Now let's take alpha between 0 and 1, and let's compute the delay time with the 2 different procedures. Why? Because he wanted to admit that there is a fast response and a slow response. He wanted to admit this. You can remove this, or you can add a third one, no problem. He said 2 ways. The first way is a linear reservoir, classical, you know it. He gets the component of the runoff that goes down and puts it into the linear reservoir, where you have a parameter. You remember the linear reservoir has a parameter, only one, a time parameter, Ks. And this is the slow component of the runoff. S stays for slow, stays for slow. But Ks is another parameter, so 2 plus alpha plus Ks, 4. And then, in the upper part, the quick runoff is routed through a cascade of 3 reservoirs. This is a classical modeling procedure in hydrology. Some people, in order to get a modification, a variant of the linear reservoir, said, why don't take a cascade of linear reservoirs with the same constant, the same time constant, Kq. This is what is called the Nash model. So he said, let's take a cascade of 3 linear reservoirs for modeling the quick runoff. Why? Because he found in the PhD thesis that in this way the quick runoff was modeled in a more refined way. You may say, why not 4, why not 5, why not 2 linear reservoirs? Because he found that 3 was the optimal. But the modeler can change this number. I did this in some applications. I put only 1 linear reservoir above, just because I thought that it was enough. So how many parameters does the model count in this way? 5. beta K, Cmax, alpha, Ks, Kq, 5 parameters. They are more than the linear reservoir, which counts only 1, but still it's a reduced number. The number of parameters is a synonym of the complexity of your model. And just keep in mind that the higher the number of parameters, the higher the complexity, the higher the flexibility, so the model is more flexible, but the higher the information that you need to run it, because these parameters have to be estimated. There are several rainfall runoff models lumped that have 7, 11 parameters, and then there are models with millions of parameters, but then the problem is the information. In hydrology, usually we don't have a lot of information available. Okay, that's it. And at this stage, I think that we know the theory because we know how to apply a linear reservoir. So we don't need to go into the details of the equations here. I just need to tell you how to compute the evapotranspiration, but there are classical procedures for doing that. At this stage, I think we can go with the code. And let me just have a look. I think the next slide may be, no, the next slide is already turning to groundwater. So let's have a look at the code. We have like 10 minutes to go. I think that we can use these 10 minutes to have a look at the code. And then if we have time, we can talk about parameter estimation, which is the next step. Actually, the next step would be groundwater models, but okay, let's see. I think I can introduce here parameter estimation because it's more directly connected to IMOD. But let me just look at the code now. Groundwater models, in any case, the next time. I don't want to do it now. Okay, this is R, so let me keep it for now. And let me go here. And I think let me, before the code, evapotranspiration, let me give you this formula here. Okay, let's look at the screen. Let's call evapotranspiration ET. This is a length per each time step. So it's an intensity actually. Millimeters per hour, typically it's millimeters per hour, millimeters per day. And let's call it ET. How can we estimate evapotranspiration? It's a bit complicated because empirical formulas, first of all, not, I mean, there are some physical models, but basically there is a large empirical basis in any formula. And it's complicated because it's a mix between evaporation and transpiration. And evaporation and transpiration both depend on water availability in the soil. If the soil is dry, you have no evapotranspiration, even if you have the same conditions. So basically, it's a process, it's a quantity that depends on the phenomena. So it depends on temperature, solar radiation, wind. Wind increases a lot the evaporation, as we know, but also depends on the water availability. So in order to estimate it, people made the first assumption. They said, let's suppose that I have enough water to be evaporated, so that the soil is has plenty of water. What is the evaporation which I may have under the assumption that I have infinite water to be evaporated? I have no water shortage in the soil. This is defined as potential evapotranspiration. It's the max evapotranspiration that you have, provided that you have enough water to be evapotranspirated. And it's called here EPT. P stands for potential. Very good. Now, it's clear that the actual evapotranspiration ET is a fraction of EP. It cannot be higher, can be zero. It's a fraction of EP. How to express this fraction? I think a logical intuition is that the fraction depends on the water storage into the catchment. This is an assumption that is adopted by many models, and it's the same assumption that you can see here. So here, first of all, you see WT. WT is the storage into the catchment. You understand why I want to compute in IMOD WT, because I have to plug in here. And what is here? Cmax divided by beta K plus 1. It's the max of WT. So at the numerator of the second addendum between the round parentheses, I repeat, at the numerator you see Cmax divided beta K plus 1. It's the max value of WT minus WT. So this difference that you see at the numerator, it's a water deficit with respect to saturation. Of course, if WT is equal to the max, you have 0 at the numerator. And then you divide it by the max of WT. So this is a measure of relative saturation. If the relative saturation is 1, then it means that WT is equal to 0. No, so my definition was not correct. What you see between round parentheses in the fraction, it's a measure of relative storage, of relative deficit of storage. Relative deficit of storage. So let's suppose that WT is equal to 0. So you don't have water to be evaporated. What are you expecting? You are expecting that ET is 0. So let's put WT equal to 0, and you see that the fraction is 1. 1 minus 1 is 0. And indeed, you get ET equal to 0. Let's suppose that WT is equal to the max value. What is the max value? Is Cmax divided by beta K plus 1. At the numerator, you have 0. The result between round parentheses is 1. So ET is equal to EPT. So depending on WT, you express ET as a fraction of EPT. This fraction is varying from 0 when WT is equal to 0 to 1 when you have saturation in the catchment. It is a linear function of WT. Clear? Okay. Now we can look at the code. So let me go back here. And if you look at the web page of our course, there is, in the exercises part, there is calibration of the IMOD rainfall runoff model, suggested our code for resolving the exercise and applying the IMOD model. This is much more than applying the model, it's calibration of it. So it means that I have to write a code that applies the model in order to find the best parameter values. This is calibration. So let's see the code. And you see that the code applies a function. Let me just increase the font. Or let me just decrease it and let me highlight the function. And then this is a function which allows me to run IMOD for the considered catchment depending on a parameter vector. And let's look how long it is, the code. It is up to here. Here there is a plot. It is up to here. It's not very long. It looks like it's long on the screen, but it's not very long because many of the lines are just definition of parameters, input data, etc. It's really not very long. And here there is a fourth cycle that applies the model at each time step. And you see that this fourth cycle is very slow, it's very short. It closes here. Here. It's very short. It's like 30 lines. There are some comments also. And I invite you, I give you an homework. Try to please have a look at this code, because next week, I would say on Thursday, we will run it. And it would be really helpful if you could have a look before running it, because you can take the most from our joint work if you already had a look at the code. If you have a look at the code, I think that there might be some lines that you don't understand, but the most of it you will understand what it does. There might be some lines that you don't understand, which we can discuss together. And but it's much better if you had a look before for the goals that I would like to reach with you by making these exercises. Next week, I would say on Thursday. Okay. I think that's it for today. Questions? Okay. So, if you have any question, meanwhile, feel free to contact me.
Thank you, Professor. Bye.
Thanks a lot. Bye-bye.